At the human scale, noise feels like the enemy. Static ruins music, background chatter drowns conversation, and measurement errors cloud our data. So it seems natural to think of Brownian noise at the microscale as just a nuisance. Tiny random kicks from solvent molecules that jostle particles and blur trajectories. But here lies a paradox. The very fluctuations that seem to spoil precision can themselves be the signal in microfluidics and nanoscience. Noise is not merely disturbance, but information in disguise. Isn't it odd that disorder can sometimes tell us more than order? Consider how physicists extract the stiffness of an optical trap. They don't pull on the bead directly. They measure how it jitters in Brownian motion, and from the variance of that noise, infer the hidden restoring force. In this case, randomness is the probe, not the problem. Similarly, single molecule biophysics relies on fluctuations to map free energy landscapes. The jumps, pauses, and wobbles of a molecule reveal the depths of its energy wells more faithfully than any static snapshot could. Noise writes the story of the underlying thermodynamics. Even more striking is the way noise can drive order. Colloidal particles sometimes self-assemble more efficiently when fluctuations help them escape local traps, a phenomenon known as stochastic resonance. In biological systems, ion channels and sensory neurons exploit noise to sharpen their sensitivity. Microfluidic droplets, buffeted by fluctuations, can align or oscillate collectively, turning randomness into synchrony. Could it be that life itself learned to thrive not despite noise, but because of it? The paradox of noise as information reshapes how we think about control. Instead of engineering ever cleaner, ever quieter systems, researchers now design experiments that harvest fluctuations. Stochastic thermodynamics even gives us equations to measure work and entropy from noisy trajectories, allowing us to treat noise as data, not dirt. In this light, Brownian motion is not a bug of the microscopic world. It is its operating system. Perhaps the most haunting thought is this: at small scales, order and disorder are not opposites but partners. Noise provides the raw material. Structure emerges by filtering, rectifying, or amplifying it. What looks like chaos in one frame becomes signal in another. The challenge for science is to learn how to listen, how to let randomness speak its hidden truths. After all, what if the universe's deepest laws are not whispered in silence, but shouted through noise? At microscales, thermal noise and Brownian motion buffet particles unpredictably, making precise control nearly impossible. Engineers traditionally regard these fluctuations as disturbances that obscure true signals. In microfluidic devices, even tiny noise can displace droplets, alter timing, or create errors in measurements. This perspective aligns with classical engineering goals of minimizing variability, where the desire for stability drives designs that filter out or average noise. Yet, in rejecting randomness, one may overlook the information hidden within it. A colloidal bead trapped by optical tweezers jitters continuously due to Brownian noise. It is like trying to watch a movie while a shaky camera keeps ruining the view. In stochastic thermodynamics, fluctuations are not nuisances, but essential observables. Noise encodes microscopic information about energy exchange, entropy production, and free energy differences. The Jarzynski and Crookes equalities show how random work distributions can recover equilibrium parameters, transforming noise into a measurable probe of hidden thermodynamic structure. Rather than obscuring laws, noise illuminates them at the nanoscale, teaching physics to see disorder as a source of order. Random fluctuations in colloid experiments verified Jarzynski's equality for non-equilibrium work. It is like decoding a message hidden in static instead of muting it. Far from equilibrium, randomness can promote structure rather than destroy it. Thermal kicks allow particles to escape local energy wells and explore broader configurations, accelerating self-assembly into ordered states. Without noise, many systems would remain stuck in metastable traps, making randomness the hidden driver that enables large-scale organization. What appears as disorder is sometimes the architect of order. DNA-coded colloids, for instance, form crystalline arrays more reliably when thermal motion helps them explore possibilities. It is like dice rolling randomly until the right numbers align to form a winning pattern. Microbiology exploits noise directly by tracking particle fluctuations to reveal material properties. The random displacements of beads provide information about viscosity, elasticity, and mechanical response, requiring no external force since noise itself supplies excitation. This makes randomness a free probe of matter. Measurements that once fought against noise now rely on it as their basis, recasting disturbance as diagnostic signal. Beads moving randomly in cytoplasm reveal the viscoelastic modulus of living cells. It is like judging the firmness of a mattress by watching how marbles bounce on it. Noise can also be rectified into useful work if combined with information and feedback. Maxwell's demon thought experiments inspired devices that harvest random motion selectively, and modern experiments confirm that feedback systems can extract work consistent with thermodynamic principles. Fluctuations thus become fuel for microscopic engines where the energy is not free, but paid for in entropy and information. Noise becomes both the obstacle and the resource. Feedback traps, for example, use Brownian kicks to lift beads against gravity, powered by information. It is like steering a canoe by catching random waves rather than paddling. Nanomotors and active colloids generate propulsion while still buffeted by thermal noise. Their trajectories are mixtures of driven motion and random fluctuations, where noise helps encode gradient directions and environmental features rather than masking signals. Analysis of noisy paths reveals hidden fields in chemical landscapes, showing how randomness complements activity in information processing. Catalytic nanomotors, for example, reveal gradient orientation through biased, noise-influenced trajectories. It is like reading wind direction from the way a flag flutters unpredictably. In groups, fluctuations spread through interactions, shaping collective dynamics. Noise can synchronize particles into ordered motion or destabilize them into chaos, with the outcome depending on coupling strength and system geometry. Randomness at the level of individuals becomes coordination at the level of swarms, and collective sensing may even rely on noise diversity to improve accuracy. Disorder enables cooperative order at scale. Flocks of bacteria align their motion, partly because random kicks seed global patterns. It is like a crowd finding rhythm from irregular claps until they all clap together. Modern engineering increasingly embraces noise as a functional input. Devices like Brownian ratchets, stochastic resonance amplifiers, and fluctuation-driven pumps intentionally exploit randomness, working not despite noise, but because of it. The physics of randomness becomes the basis for useful technologies, with microfluidics, sensing, and computing all benefiting from controlled stochasticity. Stochastic resonance, for instance, allows weak signals to be detected by adding noise at just the right level. It is like amplifying a whisper by blending it with background chatter. The paradox is that noise both limits and reveals knowledge. At one level, it destroys precision and complicates control. At another, it encodes thermodynamic, structural, and environmental information. Scientists must decide whether to suppress or exploit it depending on context, since the dual role of noise challenges simple classifications of order versus disorder. Randomness becomes the most paradoxical signal of all. Nanobubbles and active particles, for example, reveal hidden physics through fluctuations once dismissed as useless noise. It is like discovering that static on a radio carries another faint song beneath the crackle.